Okay, so let's work this problem. This is 813 out of the book. I'm going to find the slope at A, that's here at this pin connector, and the displacement in the center at C. So we're going to use conjugate beam, right? Is that what we're doing? Yeah, conjugate beam. So the first thing I need to do is solve for this structure and find the moment, and then apply the moment as load to the conjugate beam. So let's do that first. So in order to find the shear moment diagram, I'm going to solve for these values. So I'm going to assume positive shear at A and positive shear at B, and then find those values. So to do that, I'm going to sum moments. I think I'll sum moments about B. So I'm going to use my right-hand rule for sign convention, and I'm going to sum all the moments about B and make sure the structure is in equilibrium. So about B, obviously the shear at B doesn't create any moment. The 6 kilonewton force creates positive moment, and that would be that this distance is 4.5 meters. So I'll have 6 kilonewtons at 4.5 meters away. That creates positive moment. And then the shear at A will create negative moment with a moment arm of 6 meters. Well, that's convenient. The 6's cancel, so the shear at A looks to be positive 4.5 kilonewtons. That was convenient. Let's sum forces in the y direction. I'll assume up is positive, and that will give me, make sure it's in equilibrium, and then that will give me the value for the shear at B. So looking at these forces, the shear at A is up, the shear at B is down, and then I have the applied 6 kilonewton force also down. So it looks like the shear at B is going to be negative 1.5. Okay? Any questions about that? So now I can come over here and create a little template for my shear moment diagram. There's the left side and the right side. I know something's going to happen here at this 6 kip, or kilonewton force, so I'll add that in. So I'll start off with positive X. My line didn't quite get drawn. I'll assume positive shear, have the new units of kilonewtons. So what is the shear at A? It's positive 4.5. There's no load, so there's no change in shear. It stays 4.5. And of course the load is 0, so that means the slope is 0. So the shear is constant in the first 1.5 meters. And then as I go from the left side to the right side, my shear changes by 6 kilonewtons, and that's negative. So that should bring me down to minus 1.5. The change in shear over the last 4.5 meters is the area under the load curve, which is 0, so there's no change. That's nice because it matches the shear that we already computed. And of course the slope of the shear diagram is the load, which is 0. So again, 0 slope. So I have another section of constant shear. That looks like no problem, right? So now we come down to the next line. I'll assume positive X, positive moment. This will be kilonewton meter. What do we know about the moment? Well, at A, it's a pin, so I know the moment is 0. At B, it's 0. So I kind of know where I'm starting and where I'm going to end. I know the change in moment, say for this first 1.5 meters, is the area of the shear diagram, which is 4.5 times 1.5, which is 6.75. And of course the shape is given by the value of the shear, and the shear is constant and positive, so I have a constant positive slope. And then the change in moment from 1.5 to 6 is this part of the curve, which has the same value, and it's negative, brings me to 0. So that's good. And then also I see that the shear is constant and negative, so the slope constant and negative. So there's my moment diagram. So any questions about that? So now what do we do? Conjugate beam, right? So I'm going to now draw my conjugate beam. So in conjugate space, a pin in the real beam becomes what in the conjugate beam? A pin. And a roller at the end becomes a roller. So conveniently for us, the geometry of the structure is the same and the supports remain the same. I have a pin and a roller. So there's my conjugate beam. And on that I'm going to apply the moment divided by EI. So there's my moment diagram. So what I like to do is just draw the moment diagram right on the beam in the same shape. And I know that value will be 6.75 kilonewton meters. That's the moment divided by EI. In this particular problem, I forgot to write this down, but we're going to assume that EI is constant. So we're just going to drag EI around. We won't actually have to put in the value. Now this moment is positive, right? So what direction is a positive force, up or down? It is up. So in this case, the load looks like this. So now that we have this structure, I forgot the dimensions. Let me put the dimensions on here. So I've got 1.5 meters and 4.5 meters. So I need to work with this structure. Now, let's go back and check what we were asked to find. We were asked to find the slope at A, and A is here. So the slope in the real beam is what in the conjugate beam? The shear. So really I just need to find the reaction at A, and I'll have the slope at A in the real beam. The second question is, what's the displacement at C? The displacement in the real beam is what in the conjugate beam? Moment. So I need to find the moment at the center and the reaction at A. So that's going to be my strategy. So let's go ahead and make those assumptions. So I'm now going to come down here and say, well, here's my positive shear at A, and here's my positive shear at B. I'm going to find those two first, and then of course I can come back and cut the structure and decide whether I want to work left or right to find the internal moment. When I find the internal moment at the center of the beam, in the conjugate beam, that will be the displacement at C. So just to help myself out here a bit, I'm going to go ahead and label these forces. So I'm going to take this triangular load, call it F1, and I'll have another one here. Didn't give myself much room to write, but I'll call that F2. So what's F1? Well, it's a triangle, so it's going to be 1/2 the base. The base is 1.5 meters times the height, which is 6.75 kilonewton meters divided by EI. So what's that equal to? You guys are going to have to help me with that. While you're calculating that, I'll go ahead and write down what F2 is. It's also a triangular area, so that's going to be, again, 1/2 base. The base for this one is 4.5 meters. and the height is the same, 6.75 kilonewton meters divided by EI. So did somebody get the value for F1?
81 over 16.
18?
81
81?
over 16.
Oh, it's exactly 81?
No, 81 divided by 16.
Oh, 8. Well, do that for me. What's that number?
5.0625.
5.0625. Wow, that's maybe I should have done it your way, Mr. No. Sorry about that. Let's go back and do it your way. What was the fraction again? 81 over
60.
60. 60.
16 16.
16.
16. Give me the numerator.
1.
81 over
16.
16. That is really hard for me to figure out, as you can see. And that's kilonewton meters squared over 16 EI. I guess this one will be 3 times that, right? So what's 3 times 81? 243?
Yes.
So this will be 243 kilonewton meters squared over 16 EI, right? Well, that worked out nice. Thank you. Okay, I'm going to some moments about B here to find my reaction at AY. So I want all my distances from B. So what is going to be the distance D1? That's the distance from B to this. So first I'm going to travel 4.5 meters to get here, and then how far to the centroid of this triangle? A third the distance, right? And a third of 1.5 is 0.5. 0.5 to 4.5 is 5. Everybody see that? D2 from B to the centroid here will be 2/3 of this distance, and 2/3 of 4.5 is 3. Is that right? So that works out. So now I'm going to come up here. Let me draw a little line to kind of separate that. This is not a continuation. So for the conjugate beam, I'm now going to sum my moments at B and put an equilibrium. When I sum moments at B, both F1 and F2 and the shear all create what kind of moment about B? Positive or negative? Negative. So I'll just start with F1 and F2 and go that way. So F1 is going to be 81 kilonewton meters squared divided by 16 EI, and that'll have a distance of 5, and that should be negative, minus 243 kilonewton meters squared divided by 16 EI, and that's F2, and that'll have a moment arm of 3, and then the shear at A with a moment arm of 6. So what is the shear at A? I think it's going to come out negative. $200 over 16. I'm just guessing. This is the point in the video where it gets really quiet for a while you guys calculate.
It's 11.8125.
What is that over 16? Multiply that by 16. Is it a whole number?
189.
189. So 189, and that'll be kilonewton meters squared over 16 EI. Now let's see if this makes sense. How do you think this structure would deflect? Probably look like a big smiley face, right? I would say something like this. What kind of slope is that at A? Positive or negative? Negative. So that seems to match what we're saying here. And you also know that 189 divided by 16 is a pretty small number. That's going to end up being a pretty small value. I will warn you that it gets a little tricky, and you need to keep up with your units when you're using SI. Because remember, kilonewton meter squared, E is going to be given in gigapascals, and I more than likely will be given in millimeters to the fourth. So you're going to have to do a little bit of work to get all that into newtons and meters. It actually works out kind of nice. A lot of the powers cancel out, and it's not bad, but I think when you go through it, take your time and look at the units. We won't get that opportunity in this problem because EI is constant. We don't actually have numerical values. Is this the answer that you guys got? I guess I could look and see if it's in the back of the book. See how we did. See, that's number 13. It says the slope is 11.8. What's 189 divided by 16? 11.8?
Yeah, that's right.
Mr. McClanahan, you say you had 11.6 or something?
I think it was the question to see.
So I guess if you don't put the minus sign in, it would be mad at you. Does it tell you which direction?
Yeah.
Okay. Well, that's good. So now we have this. Let's see what our strategy would be. I'm going to have to cut this structure in the middle at C, and I'm either going to look at the left side or the right side. I think in this case, you'll see that the right side will be a lot easier to deal with. But it requires that you know the shear at B. So let's get that. So while I'm still working with the large free body, I'll come back and sum forces in the Y direction. And when I do that, I've got shear at A acting up, the shear at B acting down. Oops. And then both my forces F1 and F2 are up. So that would be plus 81 kilonewton meter squared over 16 EI. And then F2, which is 243 kilonewton meters squared, again over 16 EI. So what is my shear at B? I think it's going to be positive. $200 and something over 16. What do you guys get? I'm looking at the shear at B as 189. That leaves me about what, 50 here? I don't know. 120 something. What do you get?
175.
Over 16?
Yeah.
Anybody else get that? No? What was your answer again? I think it's less than that.
I got 135.
That sounds better. 135? So that's 135 kilonewton meters squared over 16 EI. And that's positive. Now, does it make sense that shear at B, which maps to the slope at B, being positive, and that seems to make sense. We have positive slope at B. So now I'm going to draw a free body diagram of C to B. So let's see if I can do that. So at C is the center, so this will be at 3 meters. The right-hand side, the shear at B, we got a positive value, so it is down. 135 kilonewton meters squared divided by 16 EI. And then I have the loading. So what's the intensity of the load right here?
4.5.
Yeah, I know it's 6.75 here over the 4.5, so I want 2/3 of that. So what's 2/3 of 4.5? Well, that's convenient. So this will be 4.5 kilonewton meters divided by EI. So all I'm really looking for here in the center is the moment. So there's my moment at C, positive bending moment. And then I'm going to need the concentrated equivalent force here. I'll call that F3. So what is F3? Well, it's a triangle. So F3 will be 1/2 the base, which is 3 meters, times the height, which is 4.5 kilonewton meters divided by EI. Is that 6.75 again? So 6.75 kilonewton meters squared divided by EI. I'm going to sum the moments at the cut to find this. So I'll need the distance from here to there. That's 1/3 the distance, and 1/3 of 3 will be 1 meter. So I think I have all my pieces. Let's see if I can squeeze it in right here. I may not be able to, but let's give it a shot. So I'm going to now sum the moments at C. That's what I have. First I have the moment at C, which is negative. About C, F3 creates positive moment, which is 6.75 kilonewton meters squared over EI at a distance of 1 meter. That's really close. Can you guys even see that? Oh yeah, you can. And then this reaction force out here is negative, so that'd be minus 135 kilonewton meters squared divided by 16 EI. That's the force, and the distance is 3 meters. So what is the moment at C? I believe it's going to be negative. Like 70 something? I'm guessing. You guys can do that for me, right? 135 times 3 divided by 16, and then subtract 6.75. What do you get? No one? Bueller?
I got negative 18.5625.
Anybody else get negative 18 point something? Yes?
Well, that's
Is it over 16?
297 over 16.
297 over 16. 297, and that will be kilonewton meter cubed over 16 EI. Is that right? So what was the fraction? What does it come out to be?
18.5625.
And the back of the book has 18.6. That's pretty close. We squeezed it in. That's some success. Okay, that took 24 minutes. But I talked a lot, so that's not too bad. I think it's a reasonable problem to do. So any more questions about that? Okay.